Alright, we're going to look at line segments, and so I have this stick here that's going to represent a line segment. And so I'm going to mark on here a measurement. I have on here a stick, and you see if we mark the stick, we can measure how long the stick is. And so the blue line is the length of the stick. So what if I break the stick? If we break the stick, we see that the two pieces will add up to the length of the original stick, even though we have a break. So we can mark right here is where the segments are. So if we label this, we can come up with an idea. If the original stick was from A to B, and maybe we have some point C, which is where we cut it, we will find that segment AB is equal to, so that's the entire segment that we started with, is equal to AC, which is the smaller stick, plus this other small stick, which is C to B. So we have this kind of equation that's made up of segments or sticks. The reason we are allowed to add in geometry in an abstract way is because we have the segment addition postulate. And this postulate allows us to do this kind of algebra with sticks in a proof. And so we can go from the idea of manipulating sticks or possibly lines to having this abstract notation of segment addition. So these are line segments because a line would go infinitely, and so this only runs from one end of my paper to the next. And so we see that starting with a big stick, we can break it into two, and the total of the two smaller sticks equal the original big stick. Okay, I'm going to do a proof based on this diagram and these givens. So we are given that AC, so from this corner to this point, and EC from the opposite corner to that point are going to be congruent segments. And then that AB, this small segment here, is going to be congruent to DE. And then we are going to have to show that BC and DC are going to be congruent to each other. So to begin my proof, we always want to start with the givens, and so we have two statements that are given, and we want to make sure that's included. So AC is congruent to EC, and furthermore, AB is congruent to DE. And that's given. Now, a good second step to do, besides writing down your givens, is to switch from congruence to equal signs so that you can use some of the algebraic type of properties when you walk through your proof. And to do that, we simply are going to use the definition of congruence. So AC has to be equal to EC, and AB is equal to DE by the definition of congruence. All right, and so we have AC and EC is the first statement about congruence, and so we also have that these lines are equal. I want to rewrite AC as the sum of the segments that make it up. So AC, as you can see, is made up of AB and BC. So I'm going to make that statement. AB plus BC is equal to AC. And I can do that because of the segment addition postulate. All right, and I can do the same thing on the other side. I started out with a statement about EC, so I'm going to do the same thing here. So EC is made up of DE and DC. And that's the same reason. So now I also want to observe that I had a statement about AB and DE. So I down here said AB was exactly equal to DE. Notice I have an AB here and a DE here. For this second one, I can substitute in AB. So I can say that EC is equal to AB plus DC. Since AB is equal to DE, I can substitute AB in here by substitution. And now I'm going to take this line and this line. Since AC is equal to EC, that means if this is AC and this is EC, they have to be equal to each other. And I can put that in there. So AB plus BC is going to be equal to AB plus DC. We'll go ahead and we'll call this substitution. And then notice that I have AB here and AB here, so I'm going to subtract an AB from both sides, just like we might do in an algebra class. And so I'm going to use subtraction property. And then we'll see we have BC is equal to DC. Notice the statement that I should be going for is the then statement. This should be the last line in my proof. I have BC is equal to DC. That's one step away from this. I need this congruence in here. So to go from equals to congruence, I'm just going to quote definition of congruence again. So BC is congruent to DC by definition of congruence. And that was what we were supposed to prove. That's the then statement here. And so we can mark this as QED or put your favorite proof mark there. And we are done with this problem. Alright, so we have this arrow type thing here and this double arrow here. And we're going to be given that this fin is congruent to this fin, that this fin is congruent to this fin, and that we have some kind of sum of parts here is equal to a sum of parts here. And we're being asked to prove that this shaft of this arrow is the same length as the shaft of this arrow, that they're congruent. So let's see if we can walk through a proof of this. So let's start with our givens, as we always need to try to do. And so I have MN is congruent to GF, PR is congruent to JK, and then I have this sum of MN plus NP plus PR is equal to GF, FJ, and JK. And those are given. Well, the next thing I'm going to do is that I'm going to turn these congruents into equality so that I can use the algebra type techniques to it. So MN is going to be equal to GF and PR is going to be equal to JK. and that is because the definition of congruence and then I'm going to, into this equation line, make my substitutions. So I have MN and PR on this side, and I have GF and JK on this side. I'm going to make these substitutions into this side and replace the GF with the MN and the JK with the PR. So the left-hand side I'm leaving alone. I'm making substitutions into the right-hand side. And that's the reason I'm going to use. And then I notice that I have an MN here on both sides, so I'm going to subtract that out. And I also notice that there's a PR on both sides, so I'm going to subtract those out. And I'm going to use subtraction property. And then I'm going to clean this up a little bit. So I have NP left on this side, and I have FJ left on this side. Notice I'm trying to prove that NP is congruent to FJ. Right now I have their equals, so how do I switch from equal to congruence? I'm going to quote definition of congruence again. So NP is congruent to FJ by definition of congruence. And at this point, we are done. This is what we were supposed to determine. You can make your proof mark.